In this practical, we'll be implementing approximate matching using the Boyer-Moore algorithm that we developed in a previous practical. So to begin with, I've pasted into this notebook all the code from Boyer-Moore. So we have all of the pre-processing code here, and then the Boyer-Moore function itself, and we're going to use this. So let's start by creating a new function. And this will take as arguments our pattern P that we're searching for, a text T that we're searching in, and a maximum number of mismatches N that we're willing to allow. And so we're going to do this using the pigeonhole principle. So we're going to divide the string P into n+1 segments, and then at least one of those segments must match perfectly against T. So let's start by finding the length of each of these segments. Just like that. And then we'll create a set of that will fill out with all of the indices where we found matches. Now say for each segment in P, so for I up to n+1, we have to calculate the bounds of P for the segment that we're searching for. And the end will just be I+1 times the segment length. But we want to make sure that we don't run past the end of P. So I'm going to take the minimum of this and the length of P.
So your segment length could either be a little bit longer or a little bit shorter than a perfectly even length of the different partitions. So you're just making up for that basically by resizing the last partition so that it makes up for it, right?
Right, because P might not be, its length might not be a perfect multiple of n+1.
Mm-hmm.
So this will make sure that we don't go past the end of the string.
Okay.
So now let's do our pre-processing and create our Boyer-Moore object. We're just going to use the substring of P that we just calculated, and we have to pass in the alphabet.
That's going to do all our Boyer-Moore pre-processing for us. It's going to make the tables for the good suffix rule and the bad character rule.
Yep. And now we can just run our Boyer-Moore algorithm. Passing in our preprocessed object and the text T. And this will return a list of places where that substring of P has matched to our text T. So now we have to step through each of those positions and make sure that the rest of P matches T with no more than n mismatches. So I'm going to say for each position M in matches, so the first thing to test is to make sure that our location doesn't let P run off either the beginning or the end of T. So I'm going to say if M is less than start, or M minus start plus length of P is greater than length of T. If either of these is true, this means that P runs off the beginning of T or past the end of T. So in this case, I'll just say continue to skip the rest of this loop. And now we need to count the number of mismatches between the rest of P and T. So I'll first compare the part of P before start, so from 0 up to start, against the corresponding positions in T. Say up to range, and from 0 to start. So increment mismatches if the character doesn't match, and if the number of mismatches is ever greater than our maximum n, then this doesn't work, so we're just going to break. So this will test the part of P before the segment that we already compared. Now we just have to compare the suffix after that segment. we'll do the same thing as in the loop above. Increment mismatches if it doesn't match. And if we found more than n mismatches, then break.
So now we've looked to the left and we've looked to the right and we've accumulated all the mismatches.
Yeah, so now let's just double check that if our number of mismatches is no more than n, then we can add this to our set all matches that we had above. And we don't want to add position m, we want to add m minus start to actually get the beginning of p. And then when this is all done, we just have to return all matches. I'll convert it to a list. So I made it as a set so that if we happen to find the same starting position from different segments in P, the set will just store that as one position. It won't store duplicates. So
right.
It won't get more than one of the same coordinate.
Yeah, for example, you might call this function allowing up to 2 edits or up to 2 mismatches, and then P might match exactly somewhere, in which case all 3 partitions of P are all going to match, and you're going to add that same element 3 times. So by making it a set, we still get back what we want, which is just that one result, that one offset where P occurs within T.
Yep. Okay, so now we've done this. Let's test it, see if it works. So I'm going to make up a P and a T. So now let's see, approximate match P, T, and we'll say up to 2 mismatches.
Let's see. What is it saying? Must be integers. So either start or end is not an integer.
Yeah.
Why would that be? Maybe one of them is a floating point. Maybe segment like this, because that is floating point division.
That's possible. Let me try just
Yeah.
converting it to an int like that and see if this works.
There you go.
Okay. So it was a problem with segment length was being stored as a float, but it needed integer indices for the array. So I just convert that to an int. So P matches against T with up to 2 mismatches in 2 places. So you can double check that this is right. You can see that from position 0, we have a mismatch here between A and C, and the last character is a mismatch between G and A. We can also, if we print starting at index 5 in T, it's AATTTG, so there's just a mismatch with the C there. So that has 1 mismatch.
Mm-hmm.
So if we were to do this with up to 1 mismatch, only one of these matches should be found. It should be the second one at 5. We see that's correct. We no longer get the match at 0 because that one had 2 mismatches. And if we allow a maximum number of mismatches of 0, we now have no matches because there's no cases where P matches T perfectly.
Right.